Cool. Okay, so let's see. Last week, over the past week and not the week prior, as I found out, you guys talked about aldol condensations, right? So, I mean, this is kind of like a big and important class of reactions that for whatever reason they save until the very end. Even though this is like, I think even traditionally, this is like the main way of carbon-carbon bond synthesis. So this one is kind of a big deal, though they just leave it off till this ending part. Yeah, but well, then I mean, the nice thing is, as you guys have probably seen from this chapter, is that like it's pure keto enolcetomerization. Like,
yeah,
everything is based around that reaction. And so like, if you've heard me stressing like every single time it comes up that that whole mechanism is important, I mean, like, this is why, is because, I mean, you just use it for everything in this chapter. So it's useful and valuable to know. Yeah, that's like the kind of big idea, but of course there's like a million named reactions and like variations on it, right? Like, everybody has their own different version of an aldol condensation. So I guess, well, it's up to you guys. We could briefly just like go over which reactions there were that you've seen, or we could get into problems. Either one works.
Do you have a preference, Paul? I feel like I could go either way.
Yeah, I don't feel strongly.
Maybe let's just go over things quickly and then we'll get into some problems.
Yeah,
sure.
Yeah, my thought was just to, if anything, mention like the names of each of these things.
Yeah.
So here, why don't I share and then zoom in. Okay. Okay. Yeah, and so I mean, the main aldol condensation, right? Remember, no. Okay. The main aldol condensation was when you have like some kind of enolate or enol, either one, and it just goes in and attacks another ketone here, right? And then at the end of the day, you get this alcohol, right? And they even teach you, oh, if you like blast this thing even harder with more base, then you'll just wind up making it into a double bond. Cool. Okay. And this is the whole this is like the entire idea. This is everything that this whole chapter is based around. And if there's any one pathway to know, it's this. But there's a lot of these variations, which is what I was mentioning. So just so we're on.
Is there a methyl missing there, or am I not understanding something?
There is.
Okay.
Yes. Good point. Yeah. And then I like, my main thought was just so we'd have our terminology all straightened out, right? So there's a Claisen condensation. And if you'll remember, this one has entirely to do with esters. So what we might take is, and the book, and I imagine Dr. Tong also had this whole long discussion about maybe he did, maybe he didn't, because it's like, it's kind of just like an annoying discussion to have about crossed Claisen condensations and like what types of Claisen reagents you could use and can't use. So, well, it's easy to do it if you're just reacting something with itself, because with Claisen condensations you have esters, right? So you might take like some kind of ester like this, and maybe like a methyl ester or a acetoester or something like this, and react it with itself, right? And so you would wind up getting something like this plus RO and the same thing, right? You form this by putting the ester in OR minus, because this way you don't wind up getting any transesterification. Like you don't swap this whole group out. You just, at worst, you just replace it with itself. So nobody, like, it doesn't bother anyone. Right. And then we go up here, come up, come back down, take off the ester. This is a lot of steps at once, but the point at the end of the day is that you wind up getting this beta ketone, beta diketone, really. I'm kind of using that terminology, which is new, right? But remember, this is the alpha position, this is the beta position relative to this carbon. Okay. Likewise, up here, we get an alpha beta unsaturated ketone. I think that's the right name for it. Or in general, just an alpha beta alkene. Yeah.
Those two arrows going from the carbonyl oxygen down and then back up. I mean, they cancel each other out, right? So do we generally show those?
It depends. If you're asked to show a mechanism, you definitely shouldn't do this. You should draw out all of the steps. I draw these two arrows one going up and one going back down because it kind of condenses the mechanism and it reminds us that like there is a tetrahedral intermediate at some point.
Okay.
If you were writing out the mechanism, you would definitely want to go all the way. Well, if you're really writing it out, then the enolate form looks like this, right? And so we kick these electrons down and then kick these over. Right? And then push these up, from which we'd wind up having this form. And then let's see, there's a carbon here, and then that forms a bond to this carbon. So we'd have an O minus, we'd have this RO over here, and then the methyl, right? And then from there, if we'd come down here and then pop this guy off. Yeah.
Okay.
So whenever I write out these sort of carbonyl substitution reactions, I always draw an up arrow and then a down arrow to remind us that there's a tetrahedral intermediate. But if this was like if this was a mechanism problem, you would be expected to draw it out in 2 steps. If this was not a mechanism problem, then nobody would care what you draw anyway, because this part is like just for our own sake.
Okay, cool.
So then after this, there's a Decman cyclization. Okay. Which this is just you're using a Claisen reaction in order to make a ring. So there's this to make a ring. Okay. There's like genuinely nothing profound about the Decman cyclization. It is exactly the same reaction. It's just that the 2 esters happen to be attached to each other. Like that's entirely it. So yeah, I think the book has some kind of example that looks like this, and then there's a very ugly carbonyl, but it doesn't hurt anybody. Something like this, right? And then you wind up getting a minus charge here, and you come here and you pop this off, and then there you go, you have a ring, right? Incredible. Yeah, so this is an example in the book, or just in general, this is what it looks like. So it's really not anything crazy. Oh, I'd written down in my notes that apparently in the book, there's some problem. It's 2240 that I would really recommend doing. But, you know, you don't need to.
2240. Okay.
Yeah. I don't know. I must have thought it was a decent problem because I wrote it down. Okay, there's a couple more. There's the malonic ester synthesis, which is very useful because we take this thing, which has these several ethyl groups. Okay. And these hydrogens here are like actually acidic because there's 2 carbonyls there, right? So we take this thing and we put it in some kind of base, right? Like whatever. And then we wind up giving it anything that you can do substitution on. Like at this point, this is just kind of normal SN2. So you do that, and then it'll replace one of these hydrogens with this R group. And from there, you could just, it's very conventional to just blast the thing with acid and heat. And then you wind up getting this substituted carboxylic acid. So you don't have to remember the mechanism. Well, maybe you do, but to use this reaction, you don't even have to think about the mechanism. You could just remember these 2 steps and throw in malonic acid, and then you wind up getting this substituted carboxylic acid, which is nice, and carbon dioxide gas, but whatever. Okay. And then there's another one of these. Aceto, it's something like, it's like a really annoying name. It's called like the acetoacetic ester synthesis, right? And you just use a slight variation on this compound. So it's just on one side, there's just a methyl, right? And you use the same 2 steps. You could probably guess that the difference is that instead of a carboxylic acid, you get a methyl ketone. So there you go. So you get a substituted methyl ketone, which is great.
And we also have the Michael.
Yeah, exactly. So that one's next. So there's the Michael edition. Okay. So in this case, you wind up taking some, what we call a Michael donor, but that's usually just, again, an enol or enolate. For example, though, you might also have like an enamine, which is just another like version of it. Enamine is usually, it can often actually form whenever you have an imine. So that's how you actually normally make them, is just you make an imine. So you can have an enamine. Though I don't know, I guess I should be I should be more generic than this. So you have an enamine, right? And or any like one of these things. And then you have a conjugated, one of these conjugated systems. Okay, and then this will come down, and then this will attack at this end instead of over here, right? And then you wind up getting, well, this counting carbons on these are always like impossible. So let's do that. So 1, 2, 3, 4, 5. So 1, 2, 3, 4, and 5 over here. Great. Right. And so we move the charge up onto here. and there's a double bond, right? Okay, but this is just an enolate. So we keto-enolthotomerize. And we wind up getting one of these really distant ketones. So this is, maybe you guys remember, so it's alpha, beta, gamma, and then what's here? Is it delta? I don't know. I don't remember. I think it's one of these. Well,
Delta
you don't
makes
really
sense
need to,
to me, but
yeah. Yeah. I don't think you really need to call it that. Anyway, the terminology might be a beta diketone, because there's two ketones, both beta to the hydrogen. But I don't remember. No, I don't think it's called that. I don't know. Whatever it's called, it doesn't really make a difference. It's one of these things, and there's a very nice long chain. Cool. Yeah. And then there's one last thing here, which is called the Robinson annulation. Okay, which is just like the Decman cyclization was a Claisen condensation to make a ring. It's just one of these to make a ring. Okay, like same deal. If you ever wind up seeing any sort of reaction that looks like this, it has a ketone, and then you know, you give it something, and at the end of the day, you wind up with another ring attached, and there's a ketone and this like kind of funky double bond that's there. This happened through a Robinson annulation. So in this case, what you always give it is like methyl vinyl ketone, which is this bad boy, and you give it base. And then in step 2, you just heat it.
for notation in this, I mean, is it acceptable just to write MVK in your experience?
Yeah, it's totally fine.
Okay, great.
Yeah. It's like a widely used abbreviation. So even if Dr. Tong didn't really use it, I can't imagine that you would lose any points for something like that. It's like a really common thing to say. Yeah. If you choose not to heat it, I think you wind up getting an alcohol here. So you get something like this.
Okay.
And then when you heat it, the alcohol winds up leaving. Yeah.
Is the carbonyl carbon always coming together with the beta carbon from the second ring?
Yes.
Okay.
Yes, it is. Specifically because methyl vinyl ketone has this one carbon at the end. This one. Yeah. Okay. Cool. Yeah, so those are the reactions that are named. Let's see if I can get all of them. Yeah. So Claisen, Decman, malonic ester, acetoacetic acid ester, Michael addition, and then Robinson annulation. Yeah, except they're all kind of just repeats of like overarchingly the same reaction. So
In general, for like the overall Claisen, one of the things that's been tough for me is keeping track of all my carbons and figuring out when there's something that's annulating, how big the ring is. The aldehyde group, if we have something, I mean, we were doing some discussion problems where the aldehyde and the ketone, the aldehyde will always be more electrophilic, right? Because it's more reactive.
yes.
Okay.
Yeah, it will be. Yeah. there's some amount to which you can control these reactions by giving it like some more reactive things or some less reactive things, or you know, you can put on like tert-butyl or benzyl groups, right? So that there's no hydrogens that you could pull off of one side. But that's why there's this whole discussion about like Claisen reactions and the fact that like, you know, there are these like crossed Claisens where you have two different things that can both form enolates, and then you wind up getting a mixture and it gets really messy. Like the more hydrogens you can pull off, like it, you know, it like multiplicatively gets larger, right? So you'll have like 2 products or like 4 products or like a billion or whatever. So yeah. But fortunately, we generally just set up Claisens so that we don't have to deal with any of that, which is good, as it should be.
Yeah, I think we really briefly went over, well, sort of briefly across Aldol.
Yeah. So it could be done, but I don't think anybody does it. Yeah. Okay. How about we let's get some questions. So here's one, which make a bit smaller so that we can see it. Okay. Question is to give an arrow pushing mechanism for this reaction, and there's some really complicated stuff here, right? So here we have LDA, and then here we have benzaldehyde being added. And this is really ugly because, I mean, there's even this like, what are these things even called anymore? I can't remember.
Epoxides, right?
Yeah, there you go. Yeah, epoxides. So we even have this epoxide here in the final molecule, right? I'm like, where the hell does that thing come from? Yeah. So I don't know. I don't know. What do you guys think?
I'm pretty intimidated by this one right off the bat.
Yep. Yeah, a little bit. It kind of brings in a lot right away. Well, okay, there's no epoxide. Well, let's see. We don't know a lot of ways of making epoxides, right? One of them is MCPBA, but we don't have that. So it must be the other way, which means, let's see, what are we doing?
So isn't it LDA is what allows us to secure the cross product of an aldol reaction?
I'm not sure what you mean entirely.
Like, I'm more confused about this aldol because like the only time I've ever seen LDA is like we've had a lab where we used LDA to like isolate a cross product of an aldol instead of like having it react with itself. But I guess these two components wouldn't create an aldol. So
I see. Yeah. Well, I guess this probably wouldn't form an aldol with itself, or wouldn't do an aldol condensation with itself, because this ester's not very great. And well, maybe it would, but we know that in this final product, this whole thing didn't do an aldol condensation with itself. So whether it would or wouldn't,
doesn't really matter.
yeah, we're not going to think about it too hard. I think actually, looking at this problem, I think it's more intimidating than it seems. Like I don't think this one is actually as bad as all the reagents and complicated parts make it out to be.
So I guess it has to be the oxygen that's attached to our benzene that's undergoing forming the little epoxide.
Yeah, right. So that's the only place that we're getting oxygen from, right? So,
Mhm.
you know, we can have like an alcohol or something, or an O minus. Right. Maybe this is like an O minus here.
Mhm. Okay, and then
And well, we're getting rid of something here, right? If we want to form an epoxide this way. So let's say the bromine is still there, right? It's possible. Maybe we just don't get rid of it.
okay, and then from that bromine leaving, then we can form our epoxide ring on that bond.
Yeah.
Okay. And before that happens, though, I really took for granted what LDA does. And does the nitrogen protect the carbonyl? Is that what that?
As far as I understand it, LDA is just like a way, it's just a base basically to deprotonate. Like I remember using it as like a way to deprotonate the I guess better way to say it is to abstract the alpha hydrogen to make the enolate. To then like go through the whole reaction. I don't remember using it for really anything other than like what you were saying before about selecting for like a cross product, but
That's
like,
kind of how I understood it too. It's just something to pull off a hydrogen without
right, like
going
all it
under
does is just
side
abstract,
reaction.
yeah, the hydrogen.
Does it pull off the alpha carbon, a hydrogen?
Yeah.
I think it does, yeah.
Yeah.
Interesting. Thank you, sir.
Yeah, sure.
Yeah. Yeah. In this case, pulling off the alpha hydrogen won't really work because it's already a final
Right. You already
hydrogen,
have
so that's
that.
really not good, right? But I mean, we can go over here because this is conjugated, so we might as well just treat it as like the ketone might as well be over here. It's like it could just the electrons can just move all along this whole thing.
Right.
So be wherever. So you know, we could very well pull off this hydrogen. So let's send in LDA to do its thing.
Oh.
Right.
Okay, so it's like basically forces an elimination.
Right, because it'll just pull off that
Yeah.
that hydrogen and form a double bond. Like that's normally how, like when we talked about it first in the lecture this past week, that's just how he formed the enolate, right? So like if you didn't have that other like double bond, then you'd be making the double bond, if that makes sense.
Yeah, gotcha. Thank you. All right.
Okay. Right. And then, well, and from there, what happens?
Is Will the double bond?
So you got to push the electrons back down from that oxygen, right? And then you can use the double bond to do the nucleophilic attack.
Oh, very
Push them
true.
over and then use that second one. Yeah.
Mhm. Okay. And well, that's it, right? In other words, if we were going retrosynthetically, we were splitting this bond to go backwards.
Yeah.
So we split the bond to go backwards there, right? And then in the forward direction, we did what is effectively a Williamson ether synthesis to make this epoxide. Although there might be a fancier name for it than that, but that's the idea. Yeah. Okay.
Cool.
Yeah. So yeah, this one's kind of like this problem's kind of scary because it has a lot, it has like this epoxide and LDA and all these things, but like at the end of the day, it wasn't that crazy. Yeah. Yeah, I think this is actually completely like comprehensive. Like I don't think there are any like steps that we kind of glossed over or anything. This is actually everything. So that's quite good. All right. We have a lot of synthesis problems now. Very fun. So there's 4 of them. So this is the first one.
So right away we know malonic.
Malonic ester synthesis, right? But malonic ester synthesis gives us what?
Carboxylic acid.
Yeah.
Yeah,
And
right.
then
It gives
maybe-
us something that's substituted like this.
Okay, so couldn't we do a we can make a carboxylic acid and then we just add an amine, right?
Just make
Okay.
an anode. Yeah.
That might be able to work, yeah.
So I say we throw on a nice cyclohexane attached to a chlorine in a first reaction, and wait,
Let's do sodium hydroxide.
yes, and then the R group would be like cyclohexane with a chlorine, right?
With a chlorine.
Doesn't have to have a
Halogen.
halogen on it.
Okay, yeah, sure.
Chlorine, bromine,
Or bromine.
either one,
Yeah.
right? It's no different. Okay. And so this will struggle, but it'll do SN2. Okay. Oh, there's a ring on here. Oh, I always do this. Okay. It's a normal ring. Okay. And then let's see. Let's blast this with heat. And probably acid. I think it's acid.
Oh yes, it's acid.
Okay.
Like the third reaction is acid, yeah.
And so here R is this thing. And so we have How's that looking?
It's looking about one amine short of an amide.
Well, the carbonyl's in the wrong spot relative to where we want it.
Oh,
It's looking, yeah, it's also looking about one carbon too long for an amide.
Oh man, this amide. Okay.
Yes. So it's going to be a bit more involved. Not too much more involved though. Oh, maybe a bit more involved. Yeah.
Are we gonna halogenate?
Like here.
Like on alpha. I don't know my next step. I'm just throwing stuff out there.
Let's see. Well, sure, I could fill in the steps here, right? So we have this reaction, the Hell-Volhard-Zielinski reaction, HVZ reaction. Do you guys remember what that involves? I can't entirely. I think it's bromine and acid.
Is it? It's a
PBR.
PBr3.
Oh, is it? Do you need bromine too, or is it just PBr3?
Both.
I think it's Br2 and
It's
PBr.
both. Wow. Okay.
Yeah.
This is
And then the
this is
second
involved.
step is water workup.
Do you need water in the first step too, or no? No, you must not.
No.
I
right?
think it's the second, yeah.
Okay. PBr3, right? And then 2, we use H3O plus. Okay. So we've halogenated. I don't know. It's going to be hard to get rid of this carbon. Are there ways to evolve off of carbonyl as a CO2 gas? Oh, so there are, but you haven't learned them yet. That's like one of the few reactions you learn next chapter. So, that is to say, yes, this actually would be viable if you use the reactions from the next chapter, but this is fairly complicated.
So what's an alternative approach to the alpha halogenation?
Well, getting rid of this carbon altogether, or I should say, getting rid of this carbon is a lot of work. So maybe we'll want to like try a
Get rid of all
different
that.
approach. Huh?
Just not do malonic acid, or use a different approach for the malonic acid. Malonic acid.
Yeah, we could try a different starting compound to give it instead of something with a ring that's already there. We do something else. So the kind of key here is that there's 2 hydrogens. Okay, so there's actually 2 that we can work with, not just 1. So it's within our rights to use both of these. If, let's say, because our end goal, right, is to make this, right? And once we're here, this is easy, right? I mean, it's not easy. It takes 2 steps, but like still, or it could take 1 step if you want to just blast it with heat. So either way, we know how to do this part, right? But we want to get here, which means at some point, you can sort of imagine where the other carbonyl used to be. So we want the other carbonyl. Well, let's see. I want to use this column, right? So at some point, the other carbonyl was over here. Like this. Okay, and then this whole thing got up and left.
And sorry, where was that coming from?
Like from this original malonic ester synthesis.
Okay.
Like when you do this malonic ester synthesis, the way it works is that
Are we gonna end up doing like an annulation type thing?
Oh, it's the other half of the malonic ester. Okay.
yeah. Let's call it.
Like, are we gonna try to make our cyclohexane ring?
Yes, we should make a ring on the molecule because that way it's, you know, it's on this carbon right here. Okay, and then, well, and this part just gets replaced with the hydrogen.
So can we use like an alkyl halide with 2 alkyls? I mean, two
2
halogens.
halogens.
Yeah.
Yeah, that is a pretty good idea. So, okay, first step, deprotonate, easy. Minus the rest of the molecule. Great. Okay, so we have this minus charge, right? This is a pretty good nucleophile right now, so let's give it something like this. Okay. Oh, I drew X's there. Why don't we be a little bit more concrete than that? Let's give it bromines. Right. We get to decide what reagents we're using, so let's just use that. Okay. Let's use red. So goodbye, one of these bromines.
Don't we need another carbon on that chain?
We might. I was just guessing.
Oh, okay, no problem.
We'll find out. We probably do. I bet you're right.
Because there need to be 5 carbons on there because it's utilizing that carbon with the 2 hydrogens of the 6th, right?
Yeah, I
Yes,
agree.
that is-
I think 5.
That is very good reasoning. There we go. Okay.
Yeah.
Yeah. So, well, this is the step where we're doing our counting anyway, right? So let's count. Use a nice blue. Here we go. 1, 2, 3, 4, and 5. So here's 1, 2, 3, 4, and 5 are going to go here. 1, 2, 3, 4, 5. Oh yeah. Right. And we draw it in this really nice suggestive way so that we can already tell what's going to happen. Right. And we have this extra hydrogen here, so we're just going to do the same thing, right? And at this point, you already know what's happening, right? So OH, and you actually don't have to even give it anything. Never mind. There's not even any intermediate step that I could skip. So we go right here. Okay.
And then can we just go ahead and do sodium hydroxide with water and then heat and acid?
Is it
Or-
sodium hydroxide? Uh, it might be either one, so it doesn't matter. Because I'd written down it's normally acid, so I can't remember, but this might be something to double check. Most things I think at this point are usually either heat or acid. It doesn't make a difference. But
It needs to be sequential though, right? These need to be separate steps.
probably, yeah. Yeah. So let's do acid here because I'm certain that acid works, but base might also work. I just can't remember though. Right. And then we're at this carboxylic acid, right? And then
Let's throw a primary amine with a bunch of heat.
yep. A lot of heat. And that'll work. Yeah. Another surefire way of doing this is just to give it SOCl2 and then give it an amine, right? And then you could be like extra confident. Because I just think in practice this synthesis route isn't used in the lab very much, but like also who cares? We're not in the lab, right?
Sure.
So yeah.
And
This is good.
so we would use the SOCl2 to make it an acid chloride as opposed to a carboxylic acid, so it'd be more reactive, right?
Yeah.
Okay, gotcha.
And then from there you just give it the amine and the amine will do its own thing. So yeah.
In the slides, I'm seeing that we use sodium hydroxide, acid, and heat
For this?
sequentially.
Okay, so you use sodium hydroxide first in this step and then
Acid, then heat.
Okay.
But they're not.
then
They're not
heat
together.
sequential.
Yeah, I see
Oh.
2 and 3.
Okay. Yeah. Makes sense. I could believe it. Yeah. This is like reasonable. If it's written down that you do acid then heat, then I would stick with that. Yeah. Remind me, are the quizzes you have open notes?
Yeah.
Yes.
Oh, okay. Well, then you don't need to worry so much about like remembering which ones can be both acid and base and which ones have to be either one, right?
Actually, I see on one of the slides that he has acid above the arrow and heat beneath it without having 1, 2 written. So it's not altogether that big a deal, I guess.
Okay. Yeah. Yeah, I also think this is well into the part of the course. I mean, it's almost the end, right? Where this sort of thing, they might like ding you on a little bit, but like, I mean, if you figured out like this part of the synthesis and all of the rest of it, right? Like, and you forgot what like this kind of minor detail, I don't think anyone's gonna give you a really hard time about that. Yeah. So this way down here has this whole place has too many carbons, so we couldn't go with this other way. Yeah. But this way was nice. It worked well. All right, let's get another one in. Here we go. So these. Oh, oops, I just pasted in the same one. There we go.
Is this a mechanistic one or just synthesis?
Synthesis.
I kind of forget the reactants we use with benzene, but I want to throw NBS at it. Would that put on a bromine? I know that happens with alkanes. You can throw NBS at it.
You might be able to use NBS to do. No, I don't think it'll work. Alkene bromination doesn't happen through radicals. It happens through EAS. So you have to make a bromine plus ion.
So we do the BR2, PBr3 thing, the HVZ.
BR2, Fe, BR3, the iron bromide.
That'll work.
What's the difference in between the PBr3 and the FeBr3?
That's a good question.
Yeah. This is a Lewis acid catalyst. So what happens in this reaction is that you have Br, right? And then let me zoom this, it's clear. And then you have Fe, Br3. And so what this does is that Lewis acids, let's see, I think steal electrons. So, right, because like N is a Lewis base and it gives its electrons. Okay, cool. So this is a Lewis acid, so it's hungry for electrons and it'll take them away. So what it might do is that,
Oh, it will activate the BR2.
yeah, and so it'll come here and then I think it'll take one of this bromine's electrons and then maybe these electrons will go here. So you'll wind up with this Br plus and then an FeBr minus, FeBr4 minus. In contrast, PBr3 is, I don't think it likes being in this minus state as much. So, oh no, what did I do? Oops. Okay.
For us, they're functionally very different. So I guess to the extent that it's practically important, I'll make sure I won't confuse the two. I'll definitely use FeBr3 and PBr3 in different contexts. Yes.
Yeah. Yeah, I think they just react much differently. Like with PBr3, whenever we've learned about it, right, we've taken like a carbonyl and I think reacted it like this, right? So we'll take one of these guys, react it here, and then kick off a bromine. And then this bromine will wind up coming back around and then reacting down here, doing some work like this. Or it might be this carbon. I don't remember. It's one of the two, right? But like whenever you attack onto PBr3, you kick off an electron or kick off a bromine, and then that bromine will wind up doing some reactive stuff. Whereas here, this is just, it just steals electrons. So in other words, it activates this bromine. Yeah. So let me make this bigger. Great. Okay, anyway, so at the end of the day, we're brominating, right? So stick on a bromine. Okay, cool.
Let's see here.
Well, I don't know. What do we want to do?
Okay.
So before you react it with that other starting material, we're gonna need to add another carbon, right? Like if we count them up, like you wouldn't be able to just react it with that bromine as it is.
Yeah. Yeah, you got a point. So we need, well, we need to add this carbon. This
Right.
carbon is just mu. Yeah. So
And we can do that by making it a Grignard reagent and having a adding a magnesium.
yeah, okay.
And then I always forget what these things are called, but it's like an aldehyde on both sides.
Formaldehyde?
There it is.
Yeah.
So if we did a formaldehyde, use that, then we would end up having a primary alcohol there. And if we felt comfortable with that bromine, we could just convert and just use FeBr3 to convert that back to a bromine if we wanted to.
This primary alcohol. And yeah, if we choose, we can make it into a bromine. That's an option.
Because then couldn't we just use LDA on our like if we use that PBr3, got that, and then if we use LDA on our other starting reactant, then couldn't we then react the two together, get our final product?
Oh, that makes sense to me.
So we can do, let's see. Okay, follows plus LDA. Right, and so we'll wind up getting an enolate at this carbon down here, and that'll be a nucleophile, so it'll attack at that carbon. Okay, cool. And so this will proceed via like SN2.
Mm-hmm.
Okay, so we have the backbone, and now what?
Wait, wouldn't
I thought we were good.
Would it not have that double bond there?
Mm-hmm.
You just gotta
Yeah.
use some heat and right to
Use heat. No, it's going to be more involved than that right now. It's not that involved, but
Okay, wait. Now, is this a case where we could use NBS because it would go on the
yes.
least substituted?
All right, alpha brominate,
Yeah,
or not alpha brominate, benzyl.
the benzyl carbon.
Yeah. Yeah, it's really easy to fall into calling things alpha and beta. I did that all the time, right? And then here, okay. And we're almost done, right? Now we do E1, so we can just hit it with some strong base.
Excellent.
Okay,
Okay, then
that works.
give us some Mg.
Could you use like a regular oxide base instead of LDA in this situation? Like could you just use OH, deep protonate?
Where on this one?
Like when, yeah.
So this is a case where LDA would be useful because in practice, when you do this, you can't isolate the enolate. Like you have to keep it there with whatever base you used.
Right.
And so, yeah. And if we had hydroxide along with this bromine in the same place, for this bromide, you'd compete with SN2.
Right. Okay.
Yeah. So this is a case where LDA counts.
What are you using below the NBS? What's
Like
the second?
H nu.
Oh, so heat, basically, or light.
Use light, UV light.
Oh, okay.
This is just one way of writing it. Yeah. Although, however you want to write light or heat, NBS doesn't actually need UV light, so I don't think so.
Okay, yeah, I don't remember NBS requiring other
Oh,
conditions.
okay. Okay,
But
yeah.
I
So you
could
could write
definitely be wrong.
heat or whatever. Either way. In
And then-
practice, I think they just put the reaction flask like on like a lamp or something, and they just let it sit there. Does this thing.
More pedantic stuff, but the LDA needs to come first in a sequence, right? And the step with the LDA, it needs to come as the first step.
Yeah. So this is like one thing. Yeah. So it does. So we could do something like take this and then so yeah, like that. Anyway, yeah. You just want to deprotonate first. Okay. You guys happy with the synthesis?
Yeah.
Yeah, sure.
Okay. Yeah. This is a valid way of doing it. Just and this is fine. Just for the sake of like getting more exposure to this stuff, I could think of another way to do this. And it'll take, I think, a bit fewer steps. So we might just mention it. So we're starting with this ring. And so, well, let's think about it retrosynthetically too, because we kind of just plunged in forward direction. So if we're doing something
Are we
like this,
always going to want to do to take off a halogen to make that double bond?
no,
Okay.
we won't. That's the thing. So the other way that we know how to make double bonds is through E2. And sorry. No, E1. Yeah, I mean E1. I think I said it wrong before too. E1, where we take off an alcohol, right? I mean, this whole chapter we're working with oxygen containing things. So, okay, it's reasonable to guess that we might take an alcohol off. So let's say that we had this alcohol. Okay. I mean, this part is easy, right? This is just acid and heat. Okay. And
Could you get that from a carboxylic acid, perhaps? No.
no, be a bit more involved. But here we have we have this carbonyl, right? And we're attaching this whole thing.
Oh, are we
alpha to
doing
the
an Aldol
carbonyl.
condensation?
So this is where we do our Aldol condensation, right? And so this compound must have come from something that had a carbonyl here. In fact, an aldehyde, because there's just a hydrogen hanging off the side here. And it came from this enolate.
Yes, okay. And could we...
So
Well,
we're making a carboxylic acid for
where?
from the benzene.
Well, we're just making an aldehyde.
Oh, and I'll
That's all we need.
making an
Right.
aldehyde from the benzene.
And making an aldehyde with just one carbon.
Oh,
benz-
Coke. You need
yeah.
Coke?
So this is Gatterman Coke, right? So we just take benzene plus whatever this laundry list of reagents is. I think you need formaldehyde. You probably need, I think you need aluminum trichloride.
Do you need carbon dioxide? I don't remember.
This one, I don't think so. I think you need carbon dioxide for making carboxylic acid with a Grignard.
Right. Okay.
In this case, I don't think so. I don't know. There's two other things. I think it's probably like chlorine gas and like, I don't know. Maybe it's like water or something. Who knows?
Oh, carbon monoxide plus hydrochloric acid, AlCl3, and CuCl.
Okay, yeah. Never mind.
To go from
These were like all
benzene
wrong.
to benzaldehyde, yeah.
CuCl, hydrochloric acid. Yeah, this is terrible. This is like the worst reaction. Along with like the Swern oxidation, these are just
Yeah.
so. Fortunately, you could just look them up, right? You don't need to remember. So we know how to make this benzaldehyde, and then over here, right, we could just hit it with LDA. And that's it. So this synthesis route is nice because, well, fewer steps, I guess. Let's see. I think here we used an aldol. Yeah, we used this thing to do an aldol condensation anyway. So, you know, it's not like only one of them went through aldol. Like they both use aldol condensations. Yeah, this one just worked nicely because at the end of the day we had this alcohol to already remove. Okay. So let's save. Oh, let's save this in this file. Great. Oh, why won't it let me zoom? Okay, great. Okay, let's get another synthesis problem. We love these. Yeah.
We're gonna
Yes.
have to do something about this ring.
Yeah, already. That was very fast. Those are faster than I even think about them or even paste the problem on. Yeah. So yes, we will. Yeah. Yeah. I was about to mention that I love this part of the semester because at this point, like, you guys know just about as much organic chemistry as I do. So like I'm really just doing these problems with you guys at this point. Like it's really not Yeah, I mean, yeah. Fun to think about. So who the hell knows what happens to that ring? Because I don't either. So let's think about it.
So we're definitely going to want, I'm assuming we want to attack the carbonyl carbon so we can break the ring somehow, but I'm trying to think about how we would do that.
This one might be easier to do retro also. Just thinking
Yeah.
like seeing that alcohol there, like obviously you're going to do a crossed aldol product.
Yeah. Yeah, that's a good idea. That's what I was starting to think too. Right. Also, I mean, we see this monster again, right? So
Right.
if we learned our lesson last time, we'll do retrosynthesis. So why don't we do that then?
Okay.
Right. We split there, right? Because we want to split the alpha beta bond. So say we have this and
And we'd have to have a negative charge on that, right? Yep. All right.
yes, yeah, exactly. Right. And this one's easy because we just hit it with LDA. How we want to make this one is a bit more involved. Yeah, this one doesn't seem as easy.
Okay. But we're technically more than halfway there.
As far as we know. Although we might not be.
Okay, so
Much easier to go from cyclopentane to cyclohexane than vice versa.
I don't even think that one's that easy. I'm a little bit stuck.
I'm trying to think what happens again to carbonyls that have like O3 or KMnO4 put onto them.
Nothing, I think. I don't think we've learned that. Because both of those will oxidize, but carbonyls are already pretty oxidized.
Mm-hmm.
So I don't think anything in that case.
Okay.
I mean, there's the ring opening metathesis, but that's a throwback when we're gonna get some like polymer or something out of that. So that's not what we want.
That sounds complicated.
Yeah.
Let's see here. But essentially, though, it is right to think that we want to use the carbonyl to break the cyclohexane.
Yeah,
Okay.
I think so. Yeah, somehow I think we want to break this bond and make this bond. I think that's our goal over here.
Okay, so we want to do something with the alpha carbon here. So anything from this chapter.
So one thought that I have, although again, this is just a suggestion and I'm not sure if it'll work, is the fact that Aldol condensations are reversible. So perhaps, possibly, with a chance, it's possible that we can do some kind of reverse reaction on this in order to break that bond.
Hmm.
But I'm not sure. So,
Doing the aldol condensation, because if we, so you're saying like reverse synthesize that to get to, like if we did an aldol condensation, so let's say like we use like H2 and palladium or something to get rid of the alkene, is that what you're saying?
well, we can't form an alkene here though, because then this carbon over here would have 5 bonds. So that won't work, but maybe we could do something else.
Okay, so if it was, could we, but is it possible that the double bond was on the other side of the, like the other alpha carbon on that carbonyl? So if we consider that alpha carbon and then we use H2 palladium from the previous step to get rid of that double bond. And then before that, it was an aldol.
Could we not have dimethyl at that position, have the carbonyl, and then add another methyl group later?
Maybe, but the thing is, we're trying to go in the reverse, and it's easy to add the methyl group on, for example, but we'd have to take it off in this case, right? Because we're trying to go to where we started from.
Yeah, I don't know how to
Going back.
selectively do that.
Oh,
Yeah.
wait, the fourth thing that would be connected to that final carbon, there's got to be something that was supposed to be there. Is there something that could
Leave
what
and
if-
make that really electrophilic or whatever.
Yeah, what if
Our
could
nucleophile
that like
electron.
be negatively charged?
Here.
Yeah.
Yeah, do something to give that a negative charge and then have it attack the carbonyl carbons somehow.
Yeah, I'm thinking about it, but I don't know what you could do. Especially on a tertiary carbon, right? Getting a negative charge on there is just like impossible.
Yeah, without a shift.
Yeah.
This is definitely possible, right?
I think so.
Okay.
That would be.
They're not giving us an impossible
tragic.
problem.
I haven't checked the answers. I could check and then guide us to the right answer, right? But then, like, you know, where's the fun in that?
I say we give it another at least 5 minutes. I think we could do this.
We must be able to figure this out, right?
Okay.
Between the 4 of us. So
I have like a different approach that I might throw out there and see how you guys feel about it.
yeah.
So I'm just thinking in like the general way that carbonyls react, right? So if you throw a nucleophile at it, that will attack at the carbonyl carbon, push the electrons up onto the oxygen. Then they come back down and they kick off the leaving group. So is like if we make a better leaving group on that side where we want to break the bond, shouldn't that theoretically open the ring? Like if we
It
added a
could,
bromine.
yeah. The thing is that the leaving group retains the electrons, right? And either way, you're gonna wind up with a minus charge on the carbon. And
Which
so
carbon?
that, I think on
On
either
the-
carbon that you try to kick off, which is why I think it'll make that really hard.
Mhm.
Okay, so
Yeah, I know. I'm trying to think too, right? Like, what can we attack this carbonyl with to open this up? But I'm not certain. So let's say okay. Let's get rid of these things. What if we try
there has to be a reaction that opens up a carbonyl on a cyclohexane.
There's
I feel like we might
gotta
have
be
done it at some point. But let's see here. Let's see. Sure.
yeah. I don't know. There might be something really clean we're missing, but so one, this is like such a bad. This is no way. This is it. If this is the way to do it, this is like annoying. But we might be able to like brominate, for example, right? And maybe the bromine will go here. I'm not sure.
Well, you can make it go there if you do like a base promoted halogenation, right? Because the other side doesn't have any hydrogens. So if you just put like bromine and base and
Sure.
water, that should
Okay.
theoretically put your bromine on that one specific right there. Yeah.
Yeah.
So that was my thought, is like doing that, and then would that make it like sort of promote that to like break open the ring when those electrons come back down? But it doesn't, I feel like I've never seen that really happen before. So
Yeah. My thought was to take this and then do and then somehow replace this with a water, even though I think that's quite hard. And then from there you could basically like do E1, except E1 is like prone to rearrangement, so you'll probably rearrange, but like that's such a terrible way of doing this.
yeah, that was my other brief thought that I had, was to
Yeah.
like make an alkene and then like oxidize it and open it with like potassium permanganate maybe. But
Yeah.
but even that, like even if you tried to make the alkene there, it would be in the wrong spot, right?
So we have,
Yeah.
I mean, we could technically move the carbonyl later. I mean, could we go for the pretending that this was an aldol condensation, have an alkene, slice it, and see what we can do from there? Or
What, have an alkene here?
yeah, if we did the alkene there and then went Sarah's route of using potassium permanganate.
Well, this is a normal arrow. Let's go this way, right?
And then, oh, wait a second. I have an idea. Oh, wait, no.
This is a messy. This is
Yeah.
messy.
But couldn't we then just get rid of that ketone? Like LiAlH for it and just be done with it, because now we have the right amount of separation on the top carboxylic acid from.
Yeah, you guys might remember, there's something that reduces just ketones and not carboxylic acids.
I have that written down. Hang on.
Isn't it ZNHG?
Is it NABH?
Something that totally gets rid of them. It might be like it was something weird. It might have been like, no, I don't think it was ozone, but it's some, no, it definitely wasn't ozone.
4 should be
Yeah,
able
that's what I was thinking of.
Yeah, reduce that
Okay.
the ketone without touching the carboxylic acid.
Yeah, it'll turn into an alcohol.
That's right.
But I thought ZNHG only reduced ketones and didn't even touch carboxylic acids.
Oh, you're right. I think the Clemenson only reduces ketones and aldehydes.
I think so. Yeah, here, I'm actually even checking from last week what we did, because one of these things, I think it's the Claisen conditions only does ketones and it doesn't do carboxylic acids. Yeah. Well, either way, we could just like, okay, say we could get rid of this alcohol altogether, which I have the impression that we'll want to do.
Okay, so now that we have this, what can we do with this carboxylic acid?
I feel like anything you do to close the ring back up again with like using the carboxylic acid functional group is going to have the O like in the ring, right? Like if you tried to do like an esterification or something, if you left that alcohol in there or whatever, like anything you try to do to close it again, you're going to incorporate your oxygen.
Unless we convert it to an acid chloride, perhaps? Because then if we got rid of that, would get rid of the alcohol, and then we might be able to reduce later on ZNHG style the ketones or aldehydes, perhaps. But
yeah, if we try giving this SOCl2 to turn any of these into acid chlorides, you'll form the anhydride. Like then we would form this probably. So this might be too many things, but
either way, it's not 5.
That's not what we want.
Okay. All
right. I'm gonna get us a hint. Because we're a bit stuck. Okay. Okay, I'm looking at what like the solutions is that we should do, and I never would have guessed this. So we were, why don't we write it out, and we could we could at least think about it. What the hell? All right. So yeah. So let's do base catalyzed or basic halogenation. So we had that, right? Which is good. And then this is like just some crazy shit. So so we're here, right? And the idea is that we want this group to go over here. Okay. I literally would never expect anyone to figure this out. Okay, so what we might do if we were like, I don't know, organic chemistry gods, we might give this more base. And so this base will come up here. It'll attack onto the carbonyl, obviously. So we'll wind up with this. Okay. Okay.
Right.
I'm just realizing what the next step is. This is insane. Okay. So we're here, right? Okay. Totally irrational thing to do. Makes complete sense why we would do it. And now we'll notice, oh, we could just form a carbonyl, right? But now there are 5 bonds on this carbon, and this bond is just going to go over here instead.
Wait,
That,
Okay, how would that like look?
yeah. How does that work?
Uh,
It just like switches sides because we have an impossible number of bonds.
well, I guess if we were to like write out the way the mechanism fully works, is that the electrons would go there. And then, I mean, we would effectively just get this.
I guess the most stable anion from that would be that like branched or that dimethyl, I guess.
Uh,
So
So it's concerted or not
yeah,
concerted?
really, it like, this really happens like at once.
Yeah, I it's a lot.
Yeah, so this really just happens in one go. This is crazy. I would not have expected that it would actually be this tertiary carbocation or carboanion, like as a sort of intermediate. Like really, I guess this rearrangement just happens like instantly, but I would not ever guess this. And then, I mean, once you're here, you can just figure your way out.
then I say we go throw some BH3 THF with H3O plus at it. And then we throw some NaOCl at it. So like revert back to an alcohol and then go to aldehyde.
Okay, yeah. Yeah, that works. I think you can no, yeah, you gotta do some work to get from the aldehyde, right?
Yeah, I don't think there's a one-step system that will convert a carboxylic acid to an aldehyde. I think you have to go alcohol then aldehyde.
Yeah, I think so. Whatever your way of choice to do this is, you know, pick your favorite. It's yeah. No, this problem's already
All right,
kind of crazy enough. So
CL, and then before that, we
This is
have-
something you really don't want to see on an exam because it will be a total time suck.
yeah,
Also, you're not
Yeah,
gonna. I mean, speaking for myself, I also wasn't gonna get there.
no, I would not have figured this out. I can't see anybody in organic chemistry too figuring this out. I don't know, maybe some real lord could manage this, but like that.
Dr. Tong as an undergrad.
Oh yes.
Yeah, dude, I don't know.
And then, okay, so real quick, sorry. So the steps, could you go really quick? I just want to write this crazy stuff down. All right, so we start by throwing NaOH and Br2 at it. NaOH and Br2. And then we throw more OH at it. I'm just gonna take a screenshot and I'll look at it later. All right, it's fine.
Okay, sure.
I'm just hoping this is not something that is reasonably expected. So
I don't think so. I
yeah,
don't think you'll be expected to do that. That was too much. So this one, okay, there's a lot of double bonds in this problem, but we could probably do it.
Could we really quickly redraw the product out? Something in my mind gets weird about when it like has CO2 and then just the substituents written out weirdly.
Yeah, I'm actually gonna keep this as OET
Sure.
because this is OET.
Mhm.
And it's a safe bet that it's the same one. So I hope so. If it's not, then well.
Honestly, I feel like at this point anything's game, and I don't trust any assumptions anymore.
You got a point. But let's pretend, let's hope that we're safe. And
You can stay positive.
yeah.
Okay,
Right.
so
can we make this into an NVK? Or not so much? So it's quite similar to the MVK, and then it's easy to annulate.
I could see it. I don't know how we would make this 10BK. I'm not sure what that would involve. This is like hard to get rid of, I think. Let's say we just let's say we just put it in water because I don't know. Well, let's not even put it in water. Let's just think, I don't know, just think about what it does with resonance. Right? There's this electron pair here. I don't know. We'll probably actually react with this enamine. I'm gonna guess. I would. That's probably a safe bet. Yeah. Well, here's my thought then. We have an enamine, right? And we have a Michael acceptor, right? It's a conjugated thing. So maybe we could just do the reaction, right? We could just take this enamine and throw this down here, throw this here, kick this up, kick this up. who knows if this is going to work, but let's just try it. Let's also count carbons to be safe. So here's 1, 2, 3, 4, and 5. So let's say we got, drawing this is going to be terrible. Let me draw this guy first. There's no minus. Here's this double bond. OET. And then we had carbon 2 and carbon 1, which now has an M methyl.
And isn't there a methyl coming off of carbon 4?
Yes, there is. So there's methyl there.
Yes.
And there's also this thing.
Nice.
Oh boy.
Okay, so we have that. Okay, and then also coming off this double bond, there's another. Okay. All right. So don't we just have to connect? So there's 1, 2, 3, 4, 5. So we just need a cyclohexane. And if we theoretically can connect that, like, if we're going in our counting scheme, are like -2 carbon, if you go down from 1, if we can get that guy to connect to carbon 4, aren't we in business?
Yes, I think we are. In fact, that's actually what I thought we should do. So why don't we then? We already have an enolate, right? So, and we have a Michael acceptor. So let's kick this up.
And then it just happens, right?
It kind of just does, yeah.
Then we could just throw H3O plus at it to, oh wait, no, we don't even have to do that.
Not yet. Let me rotate this molecule so that this is, all right, already even drawing this is just terrible. This is truly the place where numbering carbons is the most important thing ever. Like for the Robinson annulation, for example, which I think this might be a very complex form of. I promise you, numbering your carbons is good. Be safe. It's worth it. Here we go. So we have 4, 5.
So it should be a 6-membered ring. Yeah, okay. So
4 has this methyl sticking off of it. Here we have
that will be,
here's -2.
1.
Here's -1.
Yeah, I'm gonna just
1.
stick with your numbering conventions here. -1.
Okay.
5.
And 3 had nothing, 2 had nothing, 1 had an Me2, and there was a double bond that we made here.
So we connected -2 to 4.
Yes.
2, 3. Okay, things are looking okay so far. And then carbon 1 had the amine thing. Ooh. Yes. Okay.
So something stands out to me, which is that we're missing this
Right.
carbon. Okay. Did we lose a carbon, or is something just wrong in the solution? Let's see. So we had 4 carbons here. We had 1, 2, 3, 4 carbons here, and in the final product we have 1, 2, 3, 4, 5, 6, 7, 8, 9. What? Maybe this carbon isn't meant to exist, or some really complicated shit's happening.
Oh my God.
This is a tough set of problems this week.
Yeah, I'm telling you, assumptions are out the window, guys. We can't, no mistake now.
Yeah. Let's see. Wait, in this one we have 5, 7. Did we miss a carbon? Did we lose a carbon? Wait, hold on. 1, 2, 3, 4, 5, 6, 7, 8. There's definitely 8, right? We're counting correctly.
So 4. 1, 2, 3, 4. Yeah, there's only 8 carbons in this molecule. So that's 6, 7, 8. Yeah, there's 9.
I mean, there's the N-methyl. There are more carbons there, but we're not using those, obviously.
We might have missed a carbon in this process here. Although we counted, so we definitely didn't.
Yeah, because I mean, the only other carbons that we didn't number were -1 and -2 that we put in the next step. So it came out to be 8. If we don't count, like Paul said, the N-methyls. Is there a way, like, we technically could add a methyl, but no, perhaps? Yeah, I don't know how we would do that while also maintaining the ketone.
So, I think it might just be the fact that we have this enamine here. So we just give it something to react with, right? This enamine will already react on its own. So like, why don't we just give it something then, right? Like, let's move this thing. Oh, grab this. Right, I mean, we can move this up here, right? And then we already have this enamine, right? So why don't we just give it like methyl iodide or something that'll like stick a methyl on there? Right, we might as well use the enamine if we have it, and then there we go, right? There should be a double bond here now. And I don't know what you do here. You probably just give it acid and light heat to replace the imine with a carbonyl. That's probably a safe bet. Okay.
I guess those are equivalent, right?
Mm-hmm. Yeah. They're equivalent because we didn't specify any stereochemistry about this carbon. We didn't say whether this was a wedge and this was a dash or the other way around. Yeah. At this point, we're in too deep to worry about stereochemistry. I think this is a good way to do it.
Awesome.
Yes.
Cool. Well, I have to head out, Adam. Thank
Yeah.
you so much.
1 or 2. Okay. Well, these were fun problems. So
Yeah.
there's there's two more on the worksheet. There's problem 3 and 4. 3 is a mechanism. Oh, that's really nasty. 4 is a synthesis. Doesn't seem as bad. So
Okay.
try those out too anyway. But these are kind of rough. So
I remember a couple weeks ago or whatever it was, we did ask for more syntheses. I guess they really took it to heart and came up with some serious syntheses.
these are pretty.
Yeah, I hope this isn't representative of what Dr. Tong is going to give us
Okay, it can't be.
end of this week.
No, I wouldn't expect
well.
it.
We have like, there was one quiz where we had a crazy like synthesis problem though.
I remember that.
Okay. I can I might have maybe I don't know. I might have my like exam that covered this from when I took the class, and that class had reasonable problems. So I might be able to upload or I might be able to like put the problems that I had on my exam, which were pretty reasonable, on the like workshop canvas.
That'd be awesome.
If I
Yeah.
find it.
Okay.
Those are actually good to practice in reasonable problems. So
Right.
Okay.
Perfect.
cool.
Right. Thank
Okay.
you.
Awesome.
All right. Thanks so much, Adam. See you.
Yep.